Okay, so we're now moving on into the last chapter of 17C. Totally changing gears now. We're not really doing derivatives or anything like that. It's a little unit on essentially probability. Most of you will take a statistics course at some point after this class. And so statistics, probability is a big part of statistics. And so this book just gives us a little bit of practice on the basics of probability. And when you talk about probability, it becomes really important to find ways to count things, which sounds very simple, but we're talking mainly about things that would be difficult to count. For example, most people, if you've had any instruction on probability, get the idea. If you flip a two-sided coin and someone asks what's the probability that you get a heads, well, there's one way that can happen. You can get one head out of two possibilities. You could have gotten heads or tails, so the probability is 1/2. Where things get difficult, though, what would if you were flipping the coin 10 times and you wanted to find the probability that you got 4 heads or something like that? Well, then things get a little more difficult. And so 12.1 is all about principles of counting, ideas of how to count events, especially when there are lots of possibilities. So let's get started. So the first idea is called the multiplication principle. This is something many people have an intuitive idea of what this means, just have never really attached a name to it. So here's a simple example. Suppose you're planning your class schedule for next quarter and there are 4 different statistics sections, 2 bio sections, 3 chemistry sections, and 2 music sections to choose from. How many different schedules could you make in terms of, which sections of each class you could get? So one way to model this is to make a tree diagram, right? So I didn't finish the whole thing, but for example, you could first choose any one of the 4 stat sections. Let's say you chose section 1. Well, if you choose section 1, well, now you have 2 choices of bio sections to choose. So you could have chosen bio 1 or bio 2, and that would have been true for, any of these other scenarios here. Once you pick your bio sections, then you have 3 chemistry sections to choose from. So you can imagine 3 branches coming off from each of these bio sections here. And once you choose your chemistry, then you have 2 music sections to choose from. So you can kind of imagine finishing off this tree diagram. The total number of schedules you could make would be the total number of branches. For example, stats 1, bio 1, chem 1, music 1. A different one would be stats 1, bio 1, chem 2, music 1. You can, now, that would even take a while to finish off this tree diagram. But if you think about it, the total number of schedules you could make, if you just multiply, there's 4 options for stats classes you could take. So you'd have 4 possibilities there, 2 bio sections, 3 chem sections, 2 music sections. And if you multiply those all together, that's going to give you the total number of different schedules. Okay, so this is the multiplication principle is essentially, if there's 4 ways of picking stats classes, 2 ways of picking bio classes, 3 ways, you just multiply them all together, okay, to come up with the total number of different possibilities. Okay, here's one that's maybe a little more science-oriented. Suppose you were studying the effects of light and fertilizer levels on plant growth, and you're planning to study 5 different fertilizers to see how that affects plant growth at 3 different light levels, maybe low light, mid light, really high, full sun. Now, you're going to need some plants to do this, right? So at minimum, just with 5 different fertilizers and 3 light levels, you would need 15 plants just minimum, right? Just for that. Now, in science, right, it's important to, when you're studying, doing a study like this, you want to make sure that an observation that comes out is not just a fluke. It's not just a random thing. Maybe it was something else, some other factor was an influence in how the plant grew. Maybe it didn't have to do with fertilizer level or light levels. Maybe somebody watered it too much or didn't water it at all. Okay. So for each combination of fertilizer and light level, you need to have 4 replicates or duplicates that were exactly the same light level and exactly the same fertilizer. That way, any unusual observation you would expect would have happened with all 4 of the plants that were at that fertilizer level or light level, right? So then the question is, how many plants will you need? Well, again, very simple to count with the multiplication principle. I think of 3 blanks here, 1 for the fertilizer, light level, and replicates, 5 choices of fertilizer, 3 choices of light level, and 4 replicates for each one. Multiply those together, you're going to need 60 plants for this study. There we go. There's another one. So let's say, well, I've already got the answer here. You've got the genome for HIV contains 9,749 nucleotides. There are 4 different types of nucleotides. How many genomes are possible? Well, I'm seeing 9,749 blanks, each one representing a possible nucleotide. Of each one of those nucleotides, there are 4 options, right? So the multiplication principle would say you multiply 4 times itself 9,749 times. That's a lot. You're going to get 4 to the 9,749. Not going to work that out, but if you're curious, try plugging that into a calculator. That is a very, very large number. So some of you know, right, the whole idea of the genome, decoding the genome is difficult because there are lots and lots of possibilities. Okay, another topic. So those last 3 examples were the multiplication principle. Another idea in counting is this idea of permutations. Permutations are when you're counting things, possibilities, where the order matters. The number of arrangements of something is an indication that order matters. You're not just picking things, you're going to arrange them in some way. So here's an example. Let's say at the library, they have a shelf where they're going to store 4 different math books. So they're different, they're not the same. 5 different chem books and 6 different bio books. And they're going to place them on a shelf. So how many ways are there to arrange the books on the shelf? To arrange them on there? Well, there are 15 books, right? So one way, kind of thinking about the multiplication principle, is 15 slots, 1 for each book. Now on a bookshelf, the order is kind of implied here. On a bookshelf, there's a left end and a right end. So let's think of this as the left end. There's 15 choices of placing a book on the left end. Whatever book you choose, you now have 14 choices for your next book, and then 13 choices for the one after that, 12, 11. You can kind of see this. By the time you've placed down 14 books, that last book on the right end, there's only 1 book left, so you only have 1 choice there. Now 15 times 14 times 13, all the way down to 1. We recognize that from 17A, we did Taylor series. That's 15 factorial. But just a reminder, factorials, that's 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. So you start at the number, count down until you get to 1. And for reasons that were harder to explain in when we talked about factorials in Taylor series, we will be able to explain why we need to have 0 factorial. While it doesn't make sense in this definition, we're going to define that to be 1. And then I thought I'd show you, most of the time when you're answering these questions, it's totally fine to leave your answer as 15 factorial. But if you work that out, just to give you an appreciation for how big that number is, it's 1.31 times 10 to the 12th. So we're talking trillions. Just to take 15 books and line them up on a bookshelf, there are over 1 trillion ways you could arrange those books. That's a little bit surprising, right? That's a lot. Okay. Now there's twists on some of these problems here. What if we wanted to, it makes sense if you're going to arrange some math books, some chem books, and some bio books, you wouldn't want to just randomly place them on the shelf. You'd kind of want them grouped by the same subject. So what if those same 15 books, we're going to group them by the same subject? How would we count that? Well, we're going to think about the multiplication principle and permutations. Let's say we decide to put the math books on the left end. Let's do math first because math is most important. And then we're going to place our chem books, and then we'll put our bio books. Well, now I'm thinking of the multiplication principle, but I'm going to put one blank for all 4 of those math books because I know there would be 4 factorial ways of arranging those math books, right? And then the next one, I have 5 chem books. There would be 5 factorial ways of arranging those. And my 6 bio books, 6 factorial. So multiplying these together would count the number of ways of having your math books first, then your chem books, and then your bio books. But we got to think about, what if we put our math books first, and then our bio books, and then our chem books? Or maybe we put the bio books first, and then the chem, and then the math. So you see, what we have to also consider is just the number of permutations of the subjects, right? In terms of who comes first and who comes last and who's in the middle. So if you can, I've written them out right here, right? There's 6 different permutations of math, chemistry, bio. Or you could just say, hey, there's 3 subjects. How many ways to arrange 3 subjects? There would be 3 factorial. Okay, so the 3 factorial is counting this, the number of subjects. Okay, and you multiply those all together, and that gives you the total number of ways of arranging them. Okay, so the total number of arrangements of n objects. So we've seen this in the last couple problems. If you've got n objects, and the number of ways of arranging them would be n factorial. Also call those permutations. So for example, how many ways are there to arrange the letters in the word math, M-A-T-H? Well, there's 4 objects there, so it makes sense there's 4 factorial ways of doing that, which is 24. Okay, so here's a few of them. But what I want to use this for is, what if you were counting the number of ways of arranging the letters in the word data? And what's different about data is those 2 A's would be indistinguishable. We can't tell the difference between them. In other words, if you move this A over here and this one over here, to me it looks the same, right? And so that would not be counted as a different arrangement. So what we have to think about here, again, the A's are indistinguishable. So if I temporarily, said, hey, this one's A1 and this one's A2, if I switched them around and made A2 here and A1 at the end, I wouldn't know the difference. This would be counted the same. But yet, if they were treated as all 4 different letters, these would be different, right? Those would be different, but we're going to treat them as the same. So if you think about it, every arrangement I make, there would be 4 factorial ways of arranging 4 letters, but every one of those 24 arrangements has an equivalent with the A's reversed, which would not be treated any differently. So if you think about it, it's got to be half of the number of arrangements of arranging 4 letters like math. Why half? Because what we're going to do is take the 4 factorial which is the number of ways of arranging 4 objects, and divide it by 2 factorial, which is the number of arrangements of the A's, of the 2 A's. And that gives us a way now to, if we want to count the number of arrangements of a certain number of objects or letters where we have duplicates, right? Some that are the same, we now have a way to count them. Okay, the number of arrangements of the letters in the word statistics, which has 10 letters, would be 10 factorial, but we're going to divide that by 3 factorial for the, which is the number of arrangements of my 3 T's, right? Any arrangement of those 3 T's, any different way I move those around is going to look the same, right? And then 2 factorial for the 2 I's and 3 factorial for the 3 S's. All right. Another counting question. In an art contest with 10 entries, how many ways are there to award first and second and third prize? Well, we can do that just with the multiplication principle. If you just think of 3, there's 3 prizes. We have 10 choices for the first prize, 9 choices once we pick the first place winner, and then 8 choices for the third place, which comes out to be 720. But we can also think of this as a permutation. 10 times 9 times 8 is exactly what you would get if you took 10 factorial, which would represent all of those 10 entries, and divide it by 7 factorial. Okay, I kind of wrote out the 7 factorial is 7 all the way down to 1, which would cancel out in the expansion of 10 factorial, leaving you with 10 times 9 times 8. So it comes out to be the same as 10 factorial over 7 factorial, okay, or which is the same as 10 factorial over 10 minus 3 factorial. And this leads us to a more general formula for permutations. Okay, we know that if you have n objects, the number of arrangements is n factorial, but if you wanted to select k objects from a group of n objects and arrange them, then the notation, we call that p. Some books use parentheses n comma k. Our current book has a subscript, so it's p n comma k. And it's n factorial over n minus k factorial, just like we did here. We wanted to pick 3 of the 10 art entries and assign them first, second, and third place. So we wanted to arrange them. So we can use that formula. So let's practice this. Idea. So let's say we're going to form a security code with any arrangement of 4 different letters followed by 3 different digits. How many possible codes are possible? So for example, you could have ABCD and then 079 or JZYK321. Also remember that if you had ABCD 079, there are different arrangements within that, right? You have the same 4 letters and the same 3 numbers, but that's a different code. So here's how we can count those. Just think of this using the multiplication principle. In the first blank would be the number of ways, the number of permutations. You select 4 letters from the 26 letters of the alphabet, and then all of the arrangements of those 4 letters, right? Like A, B, C, D, B, A, C, D. That's what this would count. Okay, and then we're going to multiply that by the number of arrangements of 3 digits chosen from 10, right? Remember, 0 counts, right? 0 through 9 is 10 digits. So that's counting like 079, 709. It's the same 3 numbers, but we're counting the number of permutations of those 3 numbers. And if you plug that into the formula, I actually didn't work out the final answer, but I'm sure that's a very big number. All right, on the next video, we're going to talk about the other really important way of counting things, which is the idea of combinations.